father of the law of how springs work is Robert Hooke. Thus, this model is known by most people as Hooke's law. Robert lived between 1635 and 1703. He was an English natural philosopher, architect, and polymath. Between the years 1658 and 1678, Robert was experimenting with springs because he believed that it would be possible to build a clock or a stopwatch that is driven by circular springs rather than a pendulum. In 1660, Robert discovered the relationship between the force applied on a spring and its displacement when being stretched or compressed by the force. Hooke also designed a vacuum pump for natural philosopher, physicist and chemist Robert Boyle, which Boyle used in his discovery of the springiness of air, known as Boyle's law. In this video, we will explore Hooke's law and hopefully gain a basic understanding on how springs generally work. It is important to note that Hooke's law describes a model of how an ideal spring works. We therefore neglect the mass of the spring itself and the limit to when a deformed metal begins to be plastically deformed, that is, staying in its deformed state. Also, in a real spring, the elongation or displacement of the spring does not quite follow the force linearly, but rather the linear nature of the law is merely an approximation on the behavior of springs. Here we have drawn a linear spring. If you pull its other end, it will get longer, and if you push it, it will become shorter. Here we have marked the axis along which the spring works. We call the coordinate along the axis for x. The starting point of the axis and the spring itself is just above the coil of the spring. Here, x is 0 meters long. The beginning of the coordinate system is arbitrary, but setting the origin here makes everything easier. X also means the current length of the spring, marked as a dash at the axis arrow tip. The rest length is the distance between the beginning of the coil to the end of the coil, marked with x0. Thus, the rest length is x0. The first quantity related to a spring is the delta x, which we call the displacement. The displacement is defined as the coordinate x subtracted with x0, or simply the difference between the current length of the spring and its rest length. The unit of the displacement for springs acting along a one-dimensional axis is meters. The second quantity related to a spring is its stiffness, which we write as K. A large stiffness makes the spring hard to stretch out, while a small stiffness makes the spring easy to stretch. The stiffness is the same for both elongation and compression. The unit of the stiffness for one-dimensional springs is Newton per meter. The third and final quantity associated with a spring is a spring force, which is denoted by F subscript S, as in spring. The spring force is how strong the spring wants to go back to its rest length. Then, Hooke's law states that the spring force equals the stiffness times the displacement. The force has a unit, newtons. The spring is at rest when the length of the spring equals the rest length. That is the same as saying that the displacement is 0. As a consequence, the spring force is then also 0, which is in accordance with the law. If the spring force is 0 and the spring is not moving, the applied force must be equal to 0 as well, which is required by Newton's third law of motion. For example, we can set the spring stiffness to 5000 Newton per meter. This means that it takes a force of 5 kN in order to pull the spring 1 meter. Let's copy Hooke's law and then rearrange the equation such that we get the displacement as a function of the force and the stiffness. Because the spring force is zero, then the displacement will also be zero. Now we set the applied force to 50 Newton and press the play button. But first I want to remind you to like, subscribe and comment. I will try to answer all questions you might have in the comments below. Now, as we let the simulation run its course, we see that the displacement changes proportionally to the spring force until it slows down and becomes equal to the applied force, at which instant the spring has come to a halt. The displacement now reads 10 millimeters because 15 newtons divided by 5000 newton per meter is 0.01 meters. If we change the stiffness to the double of its current value, that is 10,000 newton per meter, then we observe that the displacement becomes halved. If we have a very low stiffness, then the spring gets very long under the same force. Looking at the extremes, then we can see that if the stiffness approaches zero, then the displacement goes towards infinity when any positive force is applied. Vice versa, if the spring becomes infinitely stiff, then the displacement must become zero, no matter what force is applied. Now, if we change the direction of the applied force, we observe that the spring compresses instead of stretches, and we get negative signs for both forces and the displacement value as a result. In a future episode, we shall look at how a spring behaves when a mass hangs on its other end. Thanks for watching.